Thanks for the introduction. Really Petteri, and this is joint work with my colleague from Helsinki, Huber Flores, Jonathan Hamburg, Sinli Titti Malmivirta, Augustin Chuniga, and Emil Lagerspet. And if you wonder about that Lancaster University logo, this work was done when I was sharing an affiliation with Lancaster University and the University of Helsinki. So in our talk, we look into new ways of evaluating energy efficiency, and we use for that purpose mobile thermal cameras. So it's kind of, we took the idea of HotMobile and took it extremely literally. And the kind of motivation for work has come from the point that there's increasingly many IoT and wearable devices where where you can program things, you can deploy new programs on them, but you don't have access to the power source. So then it's very difficult to assess how much energy your software solutions are taking. And even if you have a power plug, then you can monitor how much the device itself is consuming, but you might not be able to easily separate which part of that is related to your software solution. And indeed, traditionally in like mobile sensing research, what has been used is hardware power monitoring, such as the Monson power monitor here. And that requires that you can instrument this monitoring device between the power source and the device itself. The good thing about these power monitors is that they give very accurate view of instantaneous power information. However, there's also limitations that they are limited to the particular context where you're doing your measurements. The more kind of mobile solution has been to use power profiling, where you use either software sampling or hardware sampling to generate a mathematical model that relates how energy is consumed. However, these are also a bit problematic in the sense that they are very sensitive to how you sample the energy in the first place and what kind of testbed setup you were using to construct the model. So we were looking at other ways to do this, and we're taking advantage of thermal imaging, which is increasingly available these days. So there are off-the-shelf devices that incorporate thermal cameras. There are some smartphones that have this, especially the Caterpillar range of S60 and S61 phones. And then there are kind of attachable USB thermal cameras, which is the FLIR one range of thermal cameras. And it's important to notice that these are based on forward-looking infrared, which doesn't actually measure temperature directly, but thermal radiation. And usually, the cheaper devices are uncooled, which also means that the sensors get a little bit sensitive to heating of the camera as you operate them for a longer time. And while I say they're off the shelf, they are not exactly cheap. They're reasonably priced. Caterpillar S60, S61 phones cost something like $800, I would say. Their attachable USB cameras are more in the range of like $300. And how do we use this to measure energy? The general idea is very simple. We have a device that runs some application that you want to assess in terms of the energy footprint, and then we have another device which has the thermal camera, and we take thermal images of the device that runs the application. Then from the measurements we get from the thermal camera, we get an estimate of how much energy it's consuming, and this can be done using laws of thermal transfer. What's important to notice here is that there are some parameters that reflect the kind of absolute estimate we can get. So there's one term called emissivity, which relates to how much thermal radiation the material of the object we are monitoring reflects. And then there is another variable which relates to the surface area of the target object. All right. So the idea is simple. Then you might ask, does it actually work? And pardon the pun, the answer is to a degree. I know it was bad. So we did two kinds of experiments. First of all, we had a discharge experiment where we took photos of a mobile phone running YouTube, and then we looked at different battery levels, how the energy footprint, how the thermal image was changing. Then we had a separate kind of energy evaluation where we had three computationally intensive applications, and we were looking at how well we can estimate their energy. And these applications were an augmented reality application, a chess game, and a facial recognition application. And we separately evaluated they actually are energy intensive in other works. And we used two different phone models for our experiments, a Samsung Galaxy S5 and a Nexus phone. And the reason we used such old models is one of the reasons why we are doing this work. So these were kind of the newest models we could find where we had detachable battery, or we could have access to the battery, so we could get the power monitor baseline with the monsoon. And as I mentioned, thermal cameras are somewhat sensitive to heating. So what we did in the experiment also, we made sure that the device is cooled in between, so we put the phones in a fridge. So part of the reason for this project also was that when we bought a smart fridge for our IoT lab, we wondered what excuse we would have a mobile phone inside the fridge. So then we did this work. In the discharge experiment, we kept running YouTube on the devices until the device was fully empty, and we took thermal images at every 10 battery levels, so 190, 80, and so on, and compared the thermal image across these different battery levels. At every change of 10%, we took 5 images, and we calculated temperatures as averages of them. And what we noticed that the average temperature difference was about 0.77 degrees of Celsius, so there's not so much variation across these images. And this is kind of somewhat surprising in the sense that you would assume that you know that these devices have some kind of energy saving mechanism, so there's something happening inside as the battery level changes. But overall, the fact that we can get this kind of sufficiently stable, it's within the error range of the thermal camera, indicates that there is some hope for us. Okay, so then the main experiment was looking into the different applications we have. And in this case, we used 1, 3, okay, 1, 3, and 5-minute period where we took the photos, and we have the two different phones on the top and the bottom, and the different applications. And when we look at the energy footprints and compare them to against the monsoon, which is on the right, what we see is that the differences in temperature with these different applications, they reflect the relative differences in energy that we get in the monsoon. In particular, it's important to note that it's not the same on both of the devices. On the which one was which? The S5 device, the augmented reality application consumed most, followed by face recognition and then chess. And then on the Nexus device, actually, the chess application consumed almost as much as the augment. So also these differences between the footprints of the applications were preserved in this experiment. So what we can really get is that we can get relative estimates of energy of different applications, at least to a degree again. However, when we do absolute estimates, we can see that the errors are relatively large, okay, very large, but we still keep the kind of relative difference between them. The reason these errors are so large relates to the fact that when I mentioned the thermal transfer law, we need to have a very accurate estimate of the surface area and of the emissivity of the material. And currently, we don't have those estimates, so we just took some values that we thought were reasonable. However, when we do relative estimates, these factors are kind of constant, so then we can do these measurements without having to worry about how accurately we can do estimates of those parameters. And really, in order to make this into a more coherent method, something that we could really use more in the field, there are several challenges that we need to address. One of them relates to the measurement area. So the thermal footprint that we get varies across the applications in terms of which components they utilize. Like if you're using an application that runs the accelerometer versus something that uses GPS, they might be at different parts of the device. So then, in our case, we're monitoring the back cover. You would see in different parts of the image. So you need to somehow segment and take into account the different areas of the image that show heating. Another cause of concern is that in our case, we were doing pictures at fixed intervals, so we didn't have to really worry about the heating of the camera itself too much. However, if you want to really do a proper energy estimation, then you have to operate the camera continuously, in which case it starts to drift. And these errors can be mitigated by calibrating periodically. The thermal camera, it does it already. However, the kind of factory calibration is not necessarily so accurate. Thankfully, we have a solution. As a blatant self-advertising, we have a paper on Percom coming up on how to handle this calibration issue. And there are also some other challenges that I will not go into so much detail. One of them is that to get really high accurate view, you might have to have different viewpoints of the device. So we were monitoring only the backside. However, for different applications, you would assume also that things that happen on the screen have a big impact on the energy footprint. So you would need to have something monitoring the backside and the front side of the device at the same time. Additionally, I mentioned about the emissivity, so how much thermal radiation is reflected. And there are ways to kind of improve this. One of them is to kind of attach something like thermal conducting material at the backside of the device, in which case you know the thermal property is better than what's the original material of the device. But okay, so there are also some advantages in our technique. First of all, it's independent of your power source and whatever you're doing additional, like charging or discharging state of the device. For example, in the software profiles, it has a major impact if you're charging the device while you're operating it. And our approach is applicable without access to battery or power source. And in theory, it's very mobile in the sense that you just have to move the camera around so you can go around different contexts and do energy estimates in different contexts. So to summarize, we introduced a novel approach for estimating relative energy footprints of IoT devices. We're really focusing not on the energy consumption of the device, but on software solutions that run on the device that you can't really accurately measure unless you have access to the power source. And we showed that you can do relative estimate of this using thermal imaging. And we showed through feasibility benchmark that the thermal footprint stays relatively stable when we apply constant load on the device. But we also showed that when we have different intensity levels on the device, we can separate those, and the relative ordering is preserved. So, thank you very much.